screen. Okay, so before we start our meeting for today, let me just ask you guys if you have a question so far. Questions or clarification regarding with the laboratory, with our lectures, with our quizzes, anything.
Wala naman po, sir.
Okay, so what about the others? Anyone? Wala? Alright, so mahilig kayo sa wala. Alright, so if you guys don't really have a question, so I'm thankful. So hopefully, having or that doesn't having question, meaning you were able to understand everything clearly. Okay, so I hope that's the meaning of not having a question at all. Okay. All right, so let us start now with the module 4. So I hope you guys have already started writing this one, these Maxwell loops, or sometimes call this one mesh current method. Okay, but mostly 70%. Okay, we use this one, the mesh current method, instead of the Maxwell loop method. Okay. All right, so to start with, who is the founder of this one? So the founder of this one is Mr. James Clark Maxwell. So again, as usual, whoever is the inventor or the one who was able to develop or found out this theorem, so his last name will be the one to use to name that specific theorem. So generally, we call Maxwell loops current method as mesh analysis. So we actually have a lot of names when it comes to Maxwell loop. So it could be Maxwell loop current method, mesh analysis, okay, or mesh current method. Okay, so we very widely use this circuit analysis technique. So in Maxwell loops current method, first we identify all the meshes of the circuit. Okay, so in here, yes, we have the name loop, but the one that we're only considering is the meshes. Okay, so last meeting we have discussed the difference between meshes and then loops. Okay, so contains only one loop. Okay, or one loop inside of it only, but a loop it can contain one or more. Okay, so that's their major difference when it comes to mesh and then a loops. So we imagine one loop current for every mesh. So the direction of the loop currents may be arbitrary. So we could use conventional or the current flow method. So, but generally, we consider co-directional loop currents for the sake of our calculations only. Okay. So, without a further delay, let me tell you guys the difference. Okay. So, I would say that again, 80% okay of computation is super similar with the Kirchhoff's law. Okay. It's just that this one doesn't use KCL. Okay. This one is only using KVL, but with additional things in it. Okay. So later on, you will see the difference between Kirchhoff's and then Maxwell. So this current method or mesh analysis method is quite similar to the branch current method in that it uses simultaneous equations. Okay, it also uses Kirchhoff's voltage law, like what I mentioned a while ago. It also uses Ohm's law, of course. So without Ohm's law, you won't be able to verify if your answer is correct or no. Okay, in everything, even in voltage, Kirchhoff's voltage law, it's still using Ohm's law. Okay, to determine unknown currents in a network. So it differs from the branch current method in that it does not use Kirchhoff's current law. Okay, so this is the only difference that uh, we could think about when it comes to Kirchhoff's and then Maxwell. So when we see Maxwell current method, it doesn't use Kirchhoff's current law or the KCL. And it is usually able to solve a circuit with less unknown variables and less simultaneous equations. So as you guys can see right here, you already know that this is much more better. It's a lot easier, okay, a lot faster than using the Kirchhoff's law. Okay, so like for example, instead of having a five equation in Kirchhoff's law, but in Maxwell law, you will only have three equation. Okay, so of course, solving three unknowns is better than solving five unknowns. Okay, which is especially nice if you're forced to solve without a calculator. Okay, so this is also advantageous if you're not going to use your calculator, because if you have five unknowns, you cannot solve that one right away using your calculator. But having three unknowns, it's super possible, okay, to solve that one also without a calculator. Okay, but of course, it's a lot faster if you're going to use your calculator. Okay. All right, so for you to be able to see the difference, so let's have this example. Okay, so let's see how this method works on this example problem. So I believe that this is the same example that we have used in the Kirchhoff's law. So we have here the 28 volts, 4 ohms, 2 ohms, 7 volts, and then 1 ohm. Okay, which is the same with this one. Still 2 ohms under intersection. All right, so the first thing that you guys need to do is, of course, identify the loops. So as usual, the same process, just like what we have in Kirchhoff's law. So when we say loop, okay, so all in all, you could have three loops in here, okay? One, two, and then the outer loop, which is three. But then again, since we are in meshes only, so we're only going to uh, count the mesh, okay, not the loop itself. So if we're going to have a mesh, okay, not a loop, so we're only going to have two meshes. So this is the first mesh, and then this is the second mesh. So how do we identify again the flow of that mesh or of that loop? Okay, so in my case, I always base it on the outer part, okay, of the voltage source. Okay, so in here, I always go with the positive leaving, okay, polarity of the voltage source. So wherever is a positive, that is the flow of the current. So that is why we have here clockwise. Okay, but in here we have here the positive. So as you guys can see, we have here a counterclockwise flow of current. Okay, so from here going to here. Okay, and then they will intersect right here at this node, and then they'll combine at this R2 right here. Okay, so that's how we assume the polarity of your loops or meshes. So if the assumed direction of a mesh current is wrong, then the answer for that current will have a negative value. Okay, so even though that's a negative value, that is still the correct value that we are looking for. Okay, so just let's say if it's clockwise, then just make it counterclockwise and then remove the negative sign. Okay, and then you already have the correct assumption and then the correct value, okay, or the symbol of your value, okay, or of your output. So it's not negative anymore, it's now positive. Okay, so after identifying the loop, we can now label the voltage drop polarities. So of course we have here the negative, positive, and then in here, since it's a voltage drop, so we have here the positive and negative. Okay, so it is not negative and positive. Okay, since we are considering the outer or the leading symbol of the voltage source. So positive is a sign of this one, and then upon crossing this resistor right here, it will give you a voltage drop. So it will become a negative. So the same with this one right here will give you a negative sign. So that's why we have positive and negative. Okay, so the same concept on the right side. So we have a positive right here and then negative below. Okay, and then positive, negative, and then positive, negative. Okay. So are we clear so far regarding with the labelings of voltage drops, okay, with the polarities? Can you guys follow so far up to this point?
Yes, sir.
Okay. What about the others? Only two?
Yes, sir.
Okay, very good. So again, this is super similar. Whatever you guys are doing in Kirchhoff's, still the same with the Maxwell, okay, Maxwell loop method. So later on, you will see the difference. But for now, everything is super the same. Okay, whatever we are doing in the first and second steps, it's still the same right here. Okay, so that is why I am not reading most of the definitions since they are just the same. Okay, and then after that, so using Kirchhoff's voltage law, we can now step around each of these loops, generating equations representative of the component voltage drops and polarities. Okay, so in here you can identify the KVL. So we don't use KCL, okay, in Maxwell. So we go straight or we go directly to Kirchhoff's voltage law. Okay, so let's start with the first loop, first or the first mesh, the I1. So considering this one first, the voltage source, so we'll give you 28 volts, and then minus I1 times R1. So I1 and then R1, the value of R1 is 4, so it's already right here. And then going right here, so we have minus I1 times R2. So I1 times R2. Okay, so it's already 2 ohms. But as you guys can see right here, we have an additional one, which is the positive I2. Okay, so this is now, where the difference will be coming from. So if it's Kirchhoff's law only, so we only have this one, 28 minus 4I1 minus 2 times I1. Okay, but since we are talking about mesh, okay, so we now have to consider the loops or the flow of current that is going on the other side, on the I2 loop. Okay, so if you guys are going to take a look on this one, so let me just copy this one and paste it on the paint. And let me also get this one, this equation right here. Okay, so as you guys can see, we have already the 28 minus 4I1 minus 2 times I1 only, supposedly, if it's the method of Kirchhoff's. But if we're going to consider the flow of current on this one, so if you're going to analyze this one, so we have this flow of current, and then we have this flow of current on the I1. Okay, so we have that kind of setup. So as you guys can see, we have the same flow of currents. So that is why they will be added with each other. So negative I1, okay. So it will be added with this I2 also. So it will become negative I2 once you have already distributed this negative sign right here. Or let's just simply say that I1 plus I2, okay. So again, the one that we are considering here is the if they are the same flow of current or if they are not the same flow of current. So what if we have a flow of current that is, let me just remove this one for now. What if we have a flow of current? Let's say we assume that we have this kind of current in here. So basically this one is still positive negative, okay, but this one now will become positive negative positive. This one is still correct. Okay, so negative and then positive. Wait a second. Positive, negative. So it will give you a voltage drop. Positive, negative. Hmm. Bakit parang... Okay, let me just remove this one to avoid confusion. So if I will put all of the polarities right here, we have positive, negative. Yes. And then we are now dealing with the negative sign. So it's now negative and then positive. Yeah, that's correct. And then negative and then positive. So if you guys are going to take a look at this one, since in my case, I always go with the outer sign. So of course, it will give you -7. And then in here, it will give you a positive value. Okay, since we're talking about voltage drop. So uh, it could never be a negative R2 times I2. Okay, that's because they will be added with each other already. So if you wanted to make this one as a voltage drop, so this one should have a different symbol or polarity, which will make this one positive. So again, outer, outer, and then outer. So negative, I2, and then R3. Okay, so that's how it will go if we have this kind of flow of current. Okay, so oops, why are they still the same? Ah, okay. So yes, we they have the same symbol. They still have the same symbols or polarities. However, the flow of current now is going right here. Okay, and then as you guys can see, we have the current that is flowing right here going down and then right here going up. So if we have this kind of scenario, then this one now will become negative since it's now negating, okay, the value of your I1. Okay, so they will not be added with each other anymore. So to avoid confusion, you have to disregard this one. Okay, so this is only the indicator at this point only. Okay, -2 times I sub 1, and then check if they have the same flow of current. And if they are the same, then it's positive. But if they are contradicting like this one, so going down and then going up, then this one will become negative I2. Okay, So that's basically what will happen if they have different flow of current. So were you guys able to get that one so far? And how to, determine if it's negative or positive on this one? Hello, hello. Are we clear with that one? Same flow of current, they will be added with each other. Okay. But if different flow of current, then they will be subtracted, okay, with each other. So are we clear with this one, guys? Okay, because later on we're going to have a negative sign right here on the next example. But for now, since they have the same law of current, okay, so this will be uh, addition. Okay, they will be added with each other. Anyway, so going back with our original assumption, so we have this counterclockwise and then clockwise. So those two will be added with each other. So they have the same flow of current. Okay, so that is why we have this negative 2 times I1 plus I2 right here. Okay, and then equal to 0. So after that, you can now uh, distribute this one, negative 2 times I1, negative 2 times I2. Then after that, you will have this equation right here, and then you can now add the same units. So we have 2 I1s. Okay, so negative 2 I1 minus 4 I1, so it will become negative 6 I1 and then negative 2 I2. So we could say that this is now your final equation, okay, when it comes to this loop I1, okay, or mesh I1 right here. Okay, so are we clear so far with this simplified form of equation of I1? Okay, very good, Mr. Maba. Very good, Mr. Donato. What about the others? So just let me know if you guys need more time to analyze, and then maybe, I can explain it one more time on how did we come up with this kind of equation. Okay, very good. So 4 or 5 people. So I hope the others can follow, okay? Pag may 3 mesh, magiging R1 plus I2 plus I3. No, no, no. If it's, so someone is asking, so I think this is Mr. Isagani. So, sir, pag may 3 mesh, magiging R times I1 plus I2 plus I3. No, because if we have 3 mesh, okay, the setup will be, so just for example, the setup will become like this already. Okay. So let's say this is a resistor now, and then this is a voltage source, positive, negative, negative, and then like this. So let's say this is now your loop number 3. Okay. So if it's 3 meshes, then in here we still have the same assumption. Okay. It will come up with this one, and in here it will just give you another assumption wherein we're only dealing with uh, I2, okay, and then I3, okay. So wherever they are going to, let's say, meet, okay, then those are the only things that you need to consider. So for example, right here, we have I3 flowing in right here, and then we have I2 flowing in right here. So as you guys can see, we have, let's say, you're having your loops or equation in I2, so it will become I2 times, oops, my bad, it will become R, let's just say that this is R3, R4, okay, this resistor right here. So it will become R4 times I2, okay. So this one is opposing this flow of current, so this will become negative I3. Okay, so it will never become 3 uh, currents in one equation. So it's always 2 currents in one equation. Okay, so yeah. But of course, in here, you have another one wherein you're going to deal with, let's say, R2 times, they have the same flow of current, so it's I1 plus I2. So that's basically what's happening with your middle uh, part right here. So you have to deal with this one and then deal with this one also. Okay. So instead of having two equation, it will just give you three equation. Then of course three unknowns at the same time. Okay, but in here two equations and then two unknowns only. All right. So going back with our ayun na, hanggang doon na lang ang kanyang limitation. Anyway, let me just delete that one. So you will get this one as your equation number one for the I1. So the same method or same process with the I2 right here. So let's start with here first. So we have I2, okay, or resistor 2, okay, times I1 plus I2 since they have the same flow of current. And then after that, will give you negative 7, okay, and then positive I1, I2 times 1, okay. And then after that, you can distribute this 2 right here, and then it will give you this one as your final equation. Okay, so again, I'll give you maybe 20 seconds to analyze the second equation. So again, just give me a thumbs up once you were able to get this one already. Or if not, then maybe we can do this one from the scratch again, like using the paint application. Okay, so Mr. Maaba already got this one. So you can start anywhere you want. So you can start right here, negative 7 plus I2 times 1 ohm, and then plus I2 times I2 plus I1. Okay, so as long as you have the correct polarity, then even though you shuffle this one, you'll still get the same equation. So this is your second equation. So after that, you can now have this one as your final, equation for equation number one, and then equation number two. Then you can now rearrange them, okay? Wherein I1 and I1 is aligned with each other in one column only, and then I2 and I2 is aligned with each other, okay? Wherein they are in one column. So the same with the third value, okay, which is 28 and then 7. So again, your I1 will be your X, okay, if you're going to use the calculator. And then I2 will be the Y, okay, and the 28 and 7 will be the Z. So it's X, Y, and then Z. Then after that, you can use simultaneous equation, okay, or you can use the calculator already, okay. And then after that, you'll get this one as your result. So X or I1 is 5, and then Y is, or I2 is negative 1. Okay, so I would like you guys to verify this one. Okay, so please use your calculator or you can use simultaneous equation. Okay, and then please check if we have the same value. All right, so anyone who's trying to solve this one, whether we have the same result or no. Okay, so who's trying to solve this one? Baka kasi mamaya wala naman pala, naghihintay tayo sa wala. Okay, so while waiting, maybe yes, Miss Ginoran, are you trying to solve this one? So let us use simultaneous equation. So in here, I would like to solve for the I2, okay? So I'll multiply this 1 by 3, and then, okay. You can also do this one, instead of, having a negative sign right here, you can just multiply this 1 by negative 3, so that you can just add them as 1, okay? So before that, of course, we have to get the final result of this one. So 6 I sub 1 plus 2 I sub 2 is equal to 28. Okay, and then on this side, it will give you negative 6 I sub 1 plus, it's negative 6, 9 pala, 9 I sub 2, and it's equal to 7, 14, 21, negative 21. Okay, and then you can now add them. So of course, this one will be cancelled. And then 2 I sub 2 minus negative 9 I sub 2, so it will give you negative 7 I sub 2 is equal to 28 minus 21 is 7. Okay, and then you can transpose this one on the other side. I2 is equal to 7 divided by negative 7 will give you 1 ampere. Okay, my bad, negative, since negative pala to. So it's negative 1 ampere for I sub 2. Okay. And then for the I sub 1, so the same concept. So what I will do is, okay, maybe meron pa yung kanina. Yeah. Is I will eliminate now the I sub 2 for us to be able to get the value of I1. So in here, I have to multiply this 1 by 3 and this 1 by 2. Okay, by 3. And then this one is by negative 2. Okay, then let's try to solve this one. So 3 times 6 is 18. I sub 1 plus 6 I sub 2 is equal to 2856 plus 2874. How about 1624? 816. How about? I think it's 84. Let me just check. 28 times 3 is, yeah, 84. Not 74. Okay, 84. And then right here we have negative 4. What was this again? 6 times 3 is 18. 18. Negative 4 I sub 1 plus, my bad, it's negative 6 I sub 2, then equal to negative 14. Okay, then we can now add them. So 18 minus 4 is 14 I sub 1, and then we can now cancel this one, and this one is 84 minus 14 is equal to 70. Okay, so from here we can now transpose this 14 on the other side. So 70 divided by 14 will give as a result of 70 divided by 14, 5 ampere. Okay, so in here we now have negative 1 amp for the I2 and then 5 amps for the I1. Okay, so this will be a lot easier if you're going to use your calculator. Okay, in just less than a minute, you already have the value of I2 as negative 1 and then I1 as 5 ampere. Okay, so were you guys able to follow on how did we solve for the I1 and I2? Alright, so very good, Miss Maris, Mr. Tanato, Miss Ginoran. What about the others? So maybe kumakain na yung iba. Anyway, so yeah, that's it for the example number 1, okay? And then in here, they're using blah blah blah. So, oops, parang naulit. Kaya pala. And then in here, you can now write or redraw the circuit. So we have here 5 ampere, and then negative 1 ampere. So as you guys can see, we have a negative value, meaning our assumption of this flow of current right here is actually incorrect. So the correct one was actually clockwise, and then we now have a 1 ampere right here. Okay, but what about on the R2? What is the flow or the final flow of current on the R2? So if you guys are going to take a look on this one, okay, using the method of KCL just to check what is the current that is flowing on the R2 and then R3 right here. So of course for the I1 we have 5 ampere. Okay, so at this point we have 5 amps. So some will go right here, and then some tama. Okay, so some will go right here, and then some will go right here. Okay, or we already know that the current that is flowing right here is 1 amp. Okay, and then if we are going to analyze this one using KCL, so it will give you like let's just say that this is your I2. Okay, and this part right here is your I3. So and this one is your I1. So I1 minus, so it's leaving. Okay, so we have a my bad, negative 5 plus 1. But we have the same flow. Okay, entering is 5 and then entering is 1. And then right here we have, my bad. My assumption is incorrect. Okay, so this is not the uh, uh, 1 ampere right here, but the 1 ampere is right here. Okay, and then the 4 ampere, okay, will be flowing right here. Okay, so erase natin lahat. Okay. So baguhin natin lahat. Okay. So in here, the same concept with whatever we have from before. So as we all know, we have 5 ampere right here, and then some current will flow right here, and then some current will flow right here. Okay, so my bad on that one. Because what I did is I'm adding now the I2 and then the I1 at the same time. Okay. So in here, we have the I1 flowing in, and then we have here the, let's see, again, this is your I2. Okay, and then this is your I3. Okay. Okay, so sorry for that. Alright, so let me just check if you guys are already in front of your computers. So again, just give me a thumbs up. Okay. Alright, so it seems that most of you are already here. So let's now continue this one. Okay, so there is just a correction again. I've just noticed that the I2 was actually flowing in here, okay, on the R3 part. And then the one that we assume as the I3 is the one that is flowing on the R2. Okay, because going in here, as you guys can see, I sub 2 is flowing on the R3. Okay, and then since this is the third current, we could just say that this is the I1 minus I2 or the I3 itself. Okay, so to avoid confusion again, okay, though it will give us a value of, let's say, I3, which is 4 amps. Okay, and then I2, which is still I2, but the labeling is incorrect. Okay, so to avoid that one, let me just put here I sub 2, and then this one will become the I sub 3. Okay, just to make that one the same with whatever we have in here. Okay, in the redrawing the circuit. Okay, so this one is your I2, okay, which is already 1 amp, and then this is your I3, okay, that will flow on the R sub 2. So using the KCL method, okay, so going in is positive, and then leaving is negative. So we have going in for I1, which is positive, and then going in for the I2, okay, which is, my bad, going out, okay, going out for the I2, and then another going out for the I3 is equal to 0. So at this point. KCL at, let's say, node A. At node A. Okay. It's A. Okay. And then you can now put here the values of your current. So 5 for I1, and then I2 is 1 amp. Okay. And then minus I3. So 5 minus 1 is 4, minus I3 is equal to 0. So you can now transpose this one on the other side. So I3 is equal to 4 amps. Okay. So right here we have a current that is flowing, which is 4 ampere. And then right here we have a current that is flowing, which is it's 1 ampere. Okay. So basically, 4 plus 1 is also equal to 5. Okay. Entering is equal to leaving. Okay, that's basically the idea of Kirchhoff's current law. So that is the reason why we also have this one right here, I1 minus I2. So did you guys get this one so far? Okay. But then again, okay, so do not do this one, just like what we have on this example. Okay, so it would be a lot better, like for example, this is your R1, right? So just label that one as your I1. Okay, and then this is your R3. So just label this one as your I3. Okay, so the same with the R2, just label this one as your I2. Because in here, what happened here is we have the R2, but the current that is flowing is the I3. And then we have the R3, but the current that is flowing is the I2. So it's quite confusing. Okay, so yeah, I just simply followed this one. Okay, but if it's me, I will label this one as your R2, and then I'll label this one as the R3 to avoid confusion. But anyway, since that's what we already have in here, so yeah, that's yeah, the only remedy that we can have. Same with this one. So that's it for the first example. So let me now show to you guys the main advantage of mesh current analysis. So for example, we have three, or we just have this kind of circuit right here. So let me just get this one, delete this one. Okay, so if it's using Kirchhoff's law, let's see, Kirchhoff's law. This will give you Hammond equation. So if you're going to put the loop in here, so loop 1, loop number 2, loop number 3, oops, loop number 3, and then you can even have a loop on the outer, okay, like this, and then you can see that this is your uh, loop number 4, loop 2, loop number 3, and then loop number 4, okay? And then in here, you can have, let's say, the KCL at node A, and then another KCL at node B. Okay, so all in all, you're going to have a total of 6 equations. Okay, but mostly it will be reduced to 5, since we don't usually use or uh, have another equation for loop number 4. So mostly this one is being ignored. Okay, so you could see that we have a total of 5 equations. Okay, but if you're going to use the mesh current analysis, okay, mesh theorem. So again, we don't consider this loop number 4 because it has loops inside of it. And then we are not going to use KCL anymore. So it's another less 2 equation. So all in all, you're going to have 3 equations only. So loop number 1, loop number 2, and then loop number 3. Naglalag na talaga yung computer ko. Anyway, so yeah, we have 3 equations in total. So 3 unknowns, 3 equations. But unlike in here, we have 5 unknowns, 5 equations. So that is the main advantage of using mesh current analysis. Okay. So in here, first, of course, you have to label everything. So we have this assumed flow of current. So I1, I2, I3, I4, I5, and then the node A or node B, okay, or node 1 or node 2, and then the another voltage source right here. Okay, so if you're going to use Kirchhoff's, you're going to have this kind of equation. So 5 equations, 5 unknowns. Okay, but if you're going to use a mesh current analysis, this will only give you three equations and then three unknowns. Okay, so that is basically the main advantage of this one. Okay, so let's analyze this one using, okay, I think we don't have a solution for this one. Anyway, let's just analyze on how did we come up with this kind of equation so that you guys have an idea how did we come up with this one and that one. Okay, so let's start with the loop number one. Okay, so the one that we've used is the entering polarity, so negative EB1, okay, and then positive R2 times I1 plus I2. Okay, oops, nandito naman na siya. Okay, so this one is quite confusing. Mali nga pala yung ginawa ko. So we've started right here and then jump next in here. Okay, so ganun yung flow card niya. Hindi siya clockwise, but it's counterclockwise. So after this, go right here. Okay, so that's the reason why we have R2 times I1 plus I sub 2. Okay, and then again, the one that is using is the outer. Okay, ganun na lang. Kasi mula dito, ito na yung flow of current niya. Okay, nasa outer. And then outer again, that's why we have positive right here. And then we have another positive right here since the one that we're considering is the outer. Okay, so uh, that's the main disadvantage if you're using two polarities or two method. So if you're used to using the conventional method, just stick to that kind of method. Okay, forget the other method, the current method. Okay, if you're using the current method, then stick with the current method. Okay, do not mix them in, in this number, in this another number, or in this another number. Okay, so all in all, kapag conventional ka na, just use conventional. Okay, if you're using a current method, then just use current method. Okay, so in my case, I am not used to using current method. I'm more into conventional method. So that is why if we're going to come up with our own equation, okay, using my own equation also, so let's try compare. So in my case, using the KVL at loop 1, I think it's easy to use this one now, this text right here. So KVL at loop 1, okay, so it will give you the positive EB1, okay, so I'm using the outer, and then negative I1 times R1, okay, and then right here we're going to use negative R2 times I1 first, so it's always positive. So there's no way that this will become negative. So the only one that will be indicated as positive or negative is the second loop right here. Okay, so if you are going to take a look on this one, they have the same flow of current. Okay, so they will meet right here. Okay, and then as a result, they now have the same flow of current. So if they have the same flow of current, then just simply add them. Plus, okay, I2 equal to 0. Okay, so this is now your KVL at loop number 1. Okay, so let me just label this one again. So we have this flow of current right here, and then we have this flow of current right here. So they will meet at this point right here. Okay, so moving on the I sub 2, KVL at loop 2. Okay, so let's start right here first. So we have the I will still consider the outer sign. Okay, just be consistent with whatever you're doing from first. Just do that one until the end, so that you will have the correct equation and then correct answer. So we have here positive I2. Okay, oops, yeah, it's always positive. Wait a second, going right here, and then Nakakalito na kasi ang ginamit is from here to there. Okay, so let's start with the right side na lang since kapag dito medyo nakakalito. Let's start with this one first on the R4. Okay, so we have negative I2. Okay, so we are now still dealing with the outer sign. So negative I2 times, my bad, negative R4. Okay, times I sub 2. Okay, and then they have the same flow of current of your I3. So it's positive I3. Okay. And then going right here, we have negative I2 times R3. Okay. Or R3 na lang muna times I2. Okay. Just to make this one consistent. Hindi na pala consistent kasi nauna yung currents dito. Okay. Well, anyway, so okay lang yan kasi multiplication naman. And then after that, we can now go right here. We have negative, still negative I sub 2. Okay. And then right here, we have the same flow of current. Okay. R2 pala. R2, and then the same flow of current, which is I2 plus I1. I2 plus I1. Okay, equal to 0. Okay. So, yeah, that's how we've got this KVL at loop number 2. Yeah, negative R3. Negative R2. Okay, so were you guys able to follow so far on the second equation? All right, so we now have two currents right here on the R4, and then another two currents right here on the R2. Okay, after that, we can now move on to the last equation. So this one is flowing from this one, go positive, negative, positive, negative, positive, negative. Okay, so again, I'll start with this one right here, KVL at loop 3. And right here, I will still consider the outer sign. Okay, so we have negative still the outer sign, so it's negative I3 times, or R3 rather, times I3. And then as you guys can see, I2 and I3 have the same flow of current, so it's positive I2. And then minus R5 times I3 is equal to 0. Okay, so yeah, that's it for the third equation, or the loop number 3. So are we clear on how did we get this one? So from here, going here on the R4, mali pala to, hindi pala siya R3. So let me just remove this one. It should be R4. There you go. Okay, R4 times I3 plus I2. And then negative R5 times I3. Okay, so let us now try to compare if we have the same result. Okay, so in here, all you need to do to make this one the same with the first equation is just multiply this one by negative. Okay, so just multiply this one to negative, so this one will become negative, and then negative times negative will be positive. Okay, this one, and then negative times negative is now positive. So our equation number 1 is correct. Okay, and then for the equation number 2, we have, where is it, R4? So R4, negative R4. Okay, so we have the same symbols or signs. So this one doesn't need to be multiplied to negative anymore. So take note that, even though you're multiplying negative on the entire equation, so you're not changing anything. So it's safe to do that one. Okay. If you want to have a positive equation by multiplying that into negative, then it's also okay. Okay. So negative R4 times I2 plus I3, and then followed by R3 times I2, which is now this one. And then the last one is negative R2 times I2 plus I1. This one is also correct. And then for the last one, we have here R4 first. So R4. So in here we have a negative. In here we have positive. So all you need to do is multiply this one to negative, the entire equation. So this one will become positive R4 times I3 plus I2. Okay, and then next one is EB2. Okay, so this one will also become positive upon multiplying this one by negative. And this one will also become positive upon multiplying by negative. So R5 times I3, or I3 times R5. So this one is also correct. Okay. So see, even though I have the opposite method, okay, that I've used, so I've used the conventional method, but in here I think I've used the current method, we'll still arrive with the same equation, just in different uh, symbols. Okay. So, were you guys able to follow on how did we get those equations? 80%. Okay, coming from mysteries again. Anyway, so you can always go back and then read this one again and then try to analyze everything. So this one, you won't really be able to understand this one just by looking at my solution. So it would be better if you will do this one on your own, okay, using your own paper, using your own pencil or a ball pen. So with that, you're experiencing everything. Okay, so it's a lot easier to learn that way. Okay, if you're doing that one with your own way of analyzing or how to do things. Okay. Well, anyway, so that's the advantage of using the mesh current analysis. So we have another example right here, which is the unbalanced Wheatstone bridge. Okay, so we have this circuit right here, wherein so R1 is in parallel with R4, R2 is in parallel with R5, and then what else? So after solving those, you can now have a series connection with R3. But of course, we cannot do that one easily, okay? Since this one cannot be solved using an Ohm's law alone. So in here, we have to apply either Kirchhoff's law or mesh current analysis, okay? But of course, the easiest one is always the mesh current analysis. So if you guys are going to take a look at this one, we have the first loop right here, second loop, and then the third one is right here. Okay, because if you're going to consider the Kirchhoff's law, so 1, 2, 3, and then the outer loop, and then the KCL part. Let's say KCL right here, and then KCL right here. It will give you more equations. So that is not a good option to solve this kind of circuit. Okay, so here's now the third loop, okay, which is the I3. So let's now solve this one. So in here, what we did here is the just put the label, okay, of the resistor voltage drop polarities. So we've come up with this polarity, positive, negative, positive, negative. So we have the same flow of current, okay, and then right here we have positive, negative, positive, negative. So this one also the same flow of current. However, in here, as you guys can see, we have negative, positive, and then positive, negative. So we now have two different polarities. So they are opposing each other. So as usual, the other one will become negative, or the other one will be deducted on the other current. Okay, so without a further delay, let's start with the I1 first. So in here, it started with the R2 first, going to the R1. No, going to the R3. So R2, R3, and then R1. So, and in here, the one that he used is the outer sign. So it's positive uh, R2 times I1, okay, which is now this one. And then in here we have positive R3 times I1 plus I2, okay, since they have the same flow of current. And then in here we have positive R1 times I1 plus I3, okay. So it's still positive since they have the same flow of current. So I'll give you guys 20 seconds uh, to analyze and how did we come up with this equation. And then let me know once you have already understand this original form of equation. Okay, so anyone who was able to get on how did how did we get this equation? Okay, Mr. Maaba already got this one. Okay, and then Mr. Donato also already got this one. Kunti pa sir, sabi ni Mr. Carlo. Okay. So actually, this is the one thing that you must be expert with when it comes to mesh current analysis or Kirchhoff's law. You know, forming the original equation is the most crucial one. Okay, because if there is a part that for example, you instead of having here a positive, but you put here negative, uh, you know, the entire equation is already incorrect. So you will never get the correct answer. Okay, so this is the one thing that you should be careful with, and then this is the one thing that you should always double check, triple check, quadruple check. Then after that, you cannot proceed to the next step once everything is already correct. Okay, so those equation number one, equation number two, equation number three. Because after forming that one, just by applying basic algebra, you will already get this one, and then the simplified form of equation. Okay. So once you're done with this one, and you can now distribute this 100 right here, you will get 100 I sub 1 and then 100 I sub 2. The same with 150, you will get 150 I sub 1 and then 150 I sub 3. And then you can now add similar terms. Okay, and then after that, it will give you this simplified form equation, or the final form of equation of the number one. So again, just let me know once you have already understand this part. And if ever that you have a question, so please let me know so that we can verify, you know, whether this one is really correct or no. Maybe this one is incorrect. So who knows, right? But Miss Ginaran already got this one, so very good. What about you, Mr. Maaba, Mr. Donato, Miss Maris, Mr. Gonzalez, Mr. Nathaniel, Mr. Paran, Mr. Mark Jason, Mr. Francis, Mr. Cameron, Miss Gabaldon, Sophia. Okay, 70%. Okay, great. So in here, you really need a lot of practice. So try to solve 5 problems, 10 problems, just to familiarize on how to form an equation, simplify things, finding the unknowns using the uh, simultaneous equation or using your calculator. Okay. So in your exam, so it is completely up to you. Okay. So once you have come up with this equation and then the other two equations, you can already use those three equations uh, to solve it using your calculator. So I won't be needing the solution anymore. Just indicate there in your solution that via calculator or using calculator. Okay. So with that, I already know that you have used that kind of method. But if not, and I'm not seeing any competition for the I1, I2, and I3, then maybe you have used the simultaneous equation. Okay, so via elimination. So either of those two. Okay, so once you're done with this one, so the same concept with the I sub 2. Okay, but in here we've started with, where did we start? Where is the 50 right here? Ah, ito pa rin yata yung kanina. Ito yung is1 plus 1 at is2 plus 1. Okay, so this is still the one that we have on the ISA one. Okay, just more explanations on how did we come up this one. So in my part, again, I will not read this one. I will let the reading part to you guys. Okay, since kapag babasahin ko to, lalo lang tayong tatagal. Alam ko namang marunong kayo magbasa. Okay, so I'm just adding or I'm just summarizing to make our discussion faster and quicker. Okay, faster and quicker. Parehas lang naman. Redundant. Anyway, so this is now the equation number 2. So we have here the 100 first, and then 300, and then 250. So R3 first, and then going to R4, and then going to R5. Okay. And then in here, uh, so if we are going to start with R3 and then going to R4, so I'll just assume that he have used the outer symbol. Okay, from here to here, and then to there. Okay. It's quite contradicting with the flow of current, but yeah, since I'm used to conventional methods, so that's my flow of current. Okay, but still I will still follow the symbols that's being indicated here, just to to have the same symbols. So positive 100, okay, for the R3, multiplied to the I2, okay, plus I1, okay. So yeah, that's it for the second equation. And then we have here positive 300, okay, multiplied to I2 minus I3. So why minus? Since again, we have a contradicting flow of current. Okay, so we have negative positive and then positive negative. And then in here we have positive R5, okay, which is 250 times I sub 2. Okay, so again, I'll give you guys 10 to 20 seconds to analyze and how did we come up with this equation. Okay, so anyone who was able to get this one already? Okay, very good, Mr. Maaba. What about the others? Okay, very good, Mr. Donato. Now, if you're confused with, how it was done on this example, so you can do it your way, okay, but just multiply it to negative at the end just to compare if you have the same result, okay, because either way, it will give you the same answer or the same equation, okay. So if there is a part that uh, you're different with this one, let's say on the I2 or I3 or I1 or I2, then meaning maybe you did something wrong or incorrect. Okay, so just try to redo it again and until you'll arrive with this the same equation. So again, after that, just distribute this 100 on the I1 and I2, and then the 300 on the I2 and I sub 3, and then combine similar terms, and then it will give you this simplified form of equation on the I sub 2. Okay, so again, let me know once you already got this one. Okay, very good, Mr. Donato. Okay, very good, Ms. Kinaran. Okay, so moving on to the next one. Okay, so more explanations on how did we come up with this one. I'll skip that one already. So moving on to the last equation on the I3. So we're still dealing with the outer sign. So we have here positive 24, okay, minus R1 or negative 150 times I3, okay, plus I1 since they have the same flow of current. And then negative 300, okay, so this one right here, this symbol right here, negative 300 times I3 minus I sub 2 since they have an opposing flow of current. Then same process, just multiply or distribute this 150 and 300, then you will get this equation right here, and then you can now combine similar terms, and it will give you this final equation for the I sub 3. And then from there, you can now choose between two methods. It's either via calculator or using simultaneous equation. But in my case, once I have three equations or three unknowns already, I don't use simultaneous equations anymore. Though it's still possible, but it is already super hard. But it's still possible, especially if you're an expert when it comes to uh, call this one eliminating other variables just to come up with one single variable or single unknown. But in here, as long as you have the three equations and then they are correct, and then you will get this values of I1, I2, and I3 right here. Okay, so the reference of this presentation came from All About Circuits. So if you need more information, then you can visit this one. Okay. And then as a summary, as well as using mesh current analysis, we can also use node analysis to calculate the voltages around the loops. Again, reducing the amount of mathematics required using just Kirchhoff's laws. Okay, so you can also visit this one. Okay, so it's electronics tutorials. So both of them is helpful. So it's just that they have different examples and then different way of explaining about mesh current analysis. So that's actually it for the mesh current method. So we will stop here for now since we don't have enough time anymore. So we supposedly I will try to finish until the superposition theorem, but we'll just do that one next meeting. Okay, so we'll discuss superposition and then the nodal voltage analysis on this coming Tuesday next week. Okay, so that's all for now, and goodbye and thank you guys for coming. And don't forget to answer your